Good evening, everyone. The topic today I'm going to present is experimental studies on liquid level control in a two-tank non-interacting system uh, by liquid level system by using internal model based PID controller. We have this paper was done by myself, Saddamila sir, and G. Prabhakarati sir. These are my contents. Before first, liquid level control. Why do we have liquid level control? Because we need to maintain the liquid level at a certain desired point. This is generally used in most of the process industries. So this here is a basic control diagram for a liquid level control. Here main components are controlling element, set point, control variable, and process. Depending on the process, the control variable and manipulator variable changes. So the controller present here in the process generates a signal based on the reserve point, and the actuator delivers the process fluid. So because of this closed loop operation, we can compare the feedback signal to the desired point and thus obtain the control. This is the main principle which is used by liquid level control system. There are many controllers which are used. The most common one used is PID, but PID controllers are used generally because of this simple design and structure, and their tuning parameters are done by using tuning methods such as Ziegler-Nicholas and Cohen-Kuhn methods. But these are very old, but they are still used because of their ability to give the desired optimum response. But what happened is the controller which are designed by these parameters have less robust results. Robust meaning they are very sensitive to smaller changes. So to overcome that, one of the controller I have selected is IMC. IMC controller was presented by Murari and Gerard. This works on the principle that it combines both actual process and the process model and embedded into one, and consider the whole process as a robust. And the main see, this is the basic IMC basic structure. Here we have GC as controller, GP as actual process, and GP star as process model. Here we have Y dash. Here we have Y dash. This is because of the output difference between output of actual and process model, which is due to the model mismatch. This is used by IMC method, and we try to get a better control of any process. But right now, as I said, every industries are aligned towards PID. So this structure can be rearranged in this form, modified and rearranged in the form so that it resembles to conventional PID. And then after a little bit modulation in the equation, it is compared and we find the tuning parameters. Here GPID is a standard feedback controller, which is a function of actual model and IMC controller. So why especially IMC? It gives better response compared to PID, and even it gives better response than IMC controller. These are my literature review. The Al-Hassan and co-authors have investigated the performance of multiple controllers for level control of a coupled tank and compared their results to simulation. Aishwarya Lakshmi and co-authors have compared the flow rates of interacting as well as non-interacting two-tank system. The simulation showed that PID control, their PID controllers were designed by using trial and error method. And these are some of the more authors literature review I have reviewed too. The research gap I have found through all the literature review was that most of these projects are based on theoretical models and they have limited parameter variability. Then my objective, to obtain a transfer function model based on open loop response data for two-tank non-interacting liquid level system, to design the PID controllers using Cohen-Kuhn tuning method, to design the IMC based PID controller to evaluate the performance of above IMC PID and CC PID experimentally and through simulation. This is the basic setup we had in our lab. Here, this is the reservoir. This is the overhead tank. This is the process tank or second tank in which the level was controlled. This is the pressure indicators. This was the level indicator. This line. This was the level transmitter. And this is the computer which is connected to the equipment. And the equipment was maintained at a pressure of 12 to 15 psi. This is the ideal process diagram of layout of the whole my experiment. Here, the fluid was pumped through. We studied only main flow, and we did not study disturbance flow. So here, the flow was taking in this place. It was passing through HV2 valve, HV3. Then going through HV6 and then to tank 2. And this was the level transmitter, which was indicating the level in the system. Here, my manipulative value was to my control variable was to control the level in liquid tank by manipulating the flow in input flow in the first tank. We did the identification of a process. So for that, generally we use trial and error method, open row response data. The method I have used here was open loop response data. In that, what we do is the process which is already in a steady state in controller mode, we switch it to the manual mode and then let it attain a steady state. When it attains a steady state, we give a step change of a certain amount depending on the process. Then after when the step change is given, from that we note down the values till it reaches the steady state. So that gives this response curve, and depending on the process we note down the values. Then we plot a graph between process variable and time, which gives this S graph. Here we generally this generally results in first order dead time transfer function, which is calculated by this formula is Kp by calculating K steady state gain through change in process variable and step change. The open loop the transfer function we obtain is Gp is equals to Kp by Ts plus 1 e power exponential minus TdS. And this was the open loop response data I achieved by giving a step change of 5 from 0 to 5. This was, as you can see, after this was the tangent which was drawn. Then from that I found out TD, dead time and time constant. The values which I got was KT is equal to 3.334 centimeter LPH, whereas time constant 8.66 minutes and dead time 33 minutes. Finally, the transfer function I obtained was G of S is equals to H2 by Q of S is equals to 3.334 by 8.66 S plus exponential power of minus 2.33 S. And then we just found the transfer function. Here we need to find the PID parameters. So for that I used two different methods. One of the method was Cohen-Kuhn tuning method. So what we do in this we just take the basic Cohen-Kuhn tuning rules and then substitute the obtained values which we have obtained values. From that we get the parameter from Cohen-Kuhn method. The values we obtain are Kc is equals to 1.56, Ki is equals to 0.30, Kd is equals to 1.26. Then the second method is design of IMC PID controller using IMC based PID controller. Here, as I've already mentioned, the present transfer function is split in two parts. Like here, GC is equals to GC1. GC1 of S and GC2 of S. So this is split into invertible and non-invertible part. So only the GC1 is used. After that, a filter is added, and then further rearranging and then padded approximation is introduced into the equation. Further rearranging the equations, we get this final equation. From that, we get KC tuning parameter formulas for IMC PID. Then these were the formulas which we got. After that, by the steady state gain and time constant, that time we obtained in the first in the open loop restaurant data is substituted here. Here we get Ti and TID, Ti value and TD value. But for KC value, we have a filter coefficient. So for that, we take various values, or we check for the various value of filter coefficient to give to see which gives the better response. For that, the values we have selected are 0.51, 1.52. But as we see that as we improve the increase the value of lambda, we see that the response has become sluggish, but it is immune to the external disturbance. Then I had to even factorize the value by 40% to be able to use it in my lab. This is the graphical comparison of all of these values. So here we can see the lambda value which I have selected, the best out of the best response of these has it reaches the steady state easier and it has a very low overshoot. So that was the reason we selected lambda at 0.5, and these are the further comparison to reaffirm that the lambda at 0.5 is the best option we can see. As we can see that the rise time is comparatively less, and overshoot is also very less comparatively to other coefficient values. So at that, the parameter values which we get is Kc is equals to 0.023, Ki at 0.002, and Kd at 0.02. Now, now we got both the PID controller and their parametric values. Now what we do is this was a simulation software. I used MATLAB software. Sorry, I used MATLAB software to see the simulation result. This was the block diagram for that. Here this was the only difference. This here was where the parameters were entered, and the scope was the scope was used to see how the process is going on. So results and discussion. This was a compare. I have checked the steady state from 0 to 5. So my initial point was from 5. Then I gave a set point change from 5 to 10. Here I compared both CCPID and IMCPID. As you can see, this CCPID has a lot of oscillation. And it reaches a steady state very later than compared to IMC-PID. Whereas IMC has a sluggish response, but it does not have a big overshoot and it proceeds smoothly. And this is the control action for the same set point change from 5 to 10, which is between flow rate and time. This is the computer display for CC-based PID. Here, the yellow line represents the flow rate, whereas the pink line represents the control action, whereas the blue line represents the set point. We did it individually. So this was a computer display for IMC-based PID. Then when I knew that it's one single set point, I was able to attain a steady state. I wanted to try for another level. So we did it again. We did a step change from 10 to 15. And here again, we can see that even in this graph, we can see that IMC-based PID has a better response than compared to CC-PID. And then this is the control action for the same set point change from 10 to 15. This is the computer display for CC-PID. And this is a computer display for response of IMC-based PID. Then again, we even checked for other set point, which was from 15 to 20. Again, it was drawn between liquid level and second this time. So in that we can see again IMC-PID has a better response than CC-PID in terms of oscillation, even in terms of oscillation, and even reaching steady state earlier. And this is the control action for the change from 15 to 20. This is the computer display for response of CC-based PID. Step change frame from 15 to 20. This is the computer display response for IMC-based PID from 15 to 20. Now we even all these point changes in simulation in MATLAB. So as you can see, this is a simulation output response for IMC-PID and CC-PID. Here, the blue line represents CC-PID and the red line represents IMC-PID. We can see clearly that IMC-PID reaches the steady state earlier and has very low overshoot compared to CC. This is the control action for the IMC-PID and CC. This was the graph was drawn between valve opening to time. Then similarly, from a set point range from 10 centimeters to 15 centimeters. Here we can see again that IMC performs better than CC. Similar, this is the control action for 10 to 15. For a set point change from 10 to 15. This is again a set point change from 15 to 20. And here also we can see that IMC based PID has a better response than CC based PID. Controller action, I mean, this is a controller action for the IMC PID and CC PID. These are the different calculations for different parameters. This is all for the experimental comparison. This is for the experimental comparison. Here we can see that at various set points, the CC-PID, IMC-PID performs better than CC-PID in terms of settling time and overshoot. Like in the first case, the IMC-based is better. Even in second, various cases, we see that IMC-based PID is better than CC-PID, even in 15 to 20. And then even in simulation, if the values are same, we see that IMC-based PID is better than CC-PID for all three set points. In conclusion here is that I have designed for two-tank non-interacting system, and based on the experimental data and simulation data in terms of in terms of settling time and overshoot response, we see that IMC-PID based performs better than CC's PID in terms of stabilizing the level in the system. And furthermore, I would like to point out that IMC-based PID controller has better set point tracking compared to any other controller. Additionally, this method was applied to different set points to ensure redundancy and repeatability, which gives an additional evidence for higher range operability and better settling time. Thank you.